Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The azure expanse of the sea, a canvas painted with the hues of an endless sky, has captivated humanity for millennia. The reasons for its colour, however, remained a question, largely unresolved until the early 20th century. Prevailing wisdom attributed the sea's blue primarily to the reflection of the sky above, a mirror image projected upon the water's surface. This explanation, while seemingly intuitive, possessed inherent limitations that a young Indian scientist, Chandrasekhara Venkata Raman, sought to overcome. In the year 1917, Raman published a seminal paper on the molecular scattering of light in water and the colour of the sea, a crucial step in the quest to understand the source of the ocean's radiant. Raman's work directly challenged the prevailing view, positing that the blue colour stems principally from the scattering of sunlight by the water molecules themselves. The prevailing assumption that the blue was solely the sky's reflection overlooked a critical aspect of light's interaction with matter, the phenomenon of scattering. Raman recognised this as a foundational principle. His hypothesis centred on the idea that light interacts with water molecules, and that the interaction causes scattering. This scattering, he argued, imbued the water with its characteristic blue hue. His methodology built upon the groundwork laid by Tyndall, whose work on light scattering in colloidal solutions provided an essential foundation. Raman understood and expanded upon Tyndall's observations, applying them to the specific context of water. The core of Raman's approach involved observing light scattering in water samples under various conditions. He employed a series of meticulous observations, carefully documenting the colour and intensity of light scattered from different water samples. The heart of his work lies in direct observation and careful interpretation. For example, Raman noted the colours of water samples lit by a focused beam. He altered the illumination conditions, using sunlight and artificial light sources to test the effects. Raman observed that the scattered light exhibited a blue tint, even when the water was free from visible impurities. These observations provided the basis for his arguments. Raman's observations included detailed descriptions of the colour of the scattered light, the intensity of the scattering, and how these properties changed with the illumination conditions. These specific observations, meticulously documented, served as the foundation for his conclusions. The implications of Raman's work extended far beyond a mere description of the sea's colour. Raman's observations demonstrated that water molecules themselves could scatter light, and that this scattering process conferred the blue colour. This work provided a crucial step toward understanding light scattering phenomena and their role in various optical effects. While others such as Lord Rayleigh had previously explored the scattering of light by small particles, Raman's work distinguished itself by applying this concept specifically to the molecular structure of water. The application of the scattering model to water, providing clear experimental evidence, established a more precise understanding. Raman's work, therefore, represented a significant refinement and extension of existing theory. The impact of Raman's 1917 paper reveals itself when the context expands. The work laid the foundations for his later, even more groundbreaking research on the Raman effect. This work, published in 1928, demonstrated the inelastic scattering of light by molecules. The later discovery of the Raman effect, stemming from his 1917 paper, revolutionized spectroscopy and opened a new window into the molecular structure of matter. Raman's work, a genesis of his later achievements, underscored the importance of molecular scattering, the study of light scattering and its interaction with matter. A principle illuminated in his 1917 paper led to the development of vibrational spectroscopy as a versatile analytical tool. Raman's work spurred the development of advanced techniques, enabling the exploration of molecular composition. The work's enduring legacy extends to fields like materials science, chemistry, and biology. The work's reception at the time was less about outright rejection. Raman's work built on established theories and offered compelling experimental evidence, leading to widespread acceptance of his findings. The scientific community recognized the significance of his work, understanding its departure from conventional wisdom. The work, moreover, helped pave his path to international recognition, ultimately culminating in a Nobel Prize in 1930. His analysis of the sea's colour, a scientific success, demonstrated the power of careful observation. Raman's 1917 paper, while seemingly focused on a specific phenomenon, provided the groundwork for a deeper scientific journey. The work not only expanded the understanding of light scattering, but also foreshadowed the revolutionary discoveries to come. The work initiated a cascade of scientific exploration, a legacy that continues to this. The 1917 paper on the molecular scattering of light in water and the colour of the sea by Chandrasekhara Venkata Raman presented a meticulous study of light scattering in water. This investigation, remarkable for its elegance and clarity, built upon existing theories but offered compelling experimental evidence. Raman's work departed from assumptions about the sea's color. He provided a foundation for understanding the interaction of light with matter. The paper, rich in detail, provides a clear picture of Raman's experimental setup. Its findings became foundational for subsequent spectroscopic techniques. Raman's central claim revolved around the scattering of light by water molecules. Prevailing theories often attributed color to suspended particles or impurities. Raman, however, proposed a mechanism where light interacted with the water molecules, acting as individual scattering centers. To substantiate this, he designed a simple yet effective apparatus. His apparatus primarily utilized readily available components. A light source illuminated a water sample. The scattered light was analyzed using a spectroscope. This enabled him to observe and measure the intensity and spectral distribution of the scattered light. The core of his experimental methodology involved careful observation and measurement. Raman used sunlight, passing it through a filter to isolate a particular wavelength. He meticulously examined the light scattered at different angles. He quantified the intensity of the scattered light, noting its variation with angle. Raman's data revealed that the scattered light possessed a specific spectral distribution. He observed that the blue light was scattered more efficiently than the red light. This observation proved crucial in understanding the color of the sea. These findings directly challenged the then prevalent theories. Raman's mathematical and physical reasoning underpinned this interpretation of the scattering process. He drew upon Rayleigh's theory of scattering. Rayleigh's research detailed the scattering of light by particles smaller than the wavelength of light. Raman adapted this theory to describe the scattering of light by water molecules. He viewed each water molecule as a small, independent scattering entity. Rayleigh's work assumed particles that were isotropic. In his work, Raman explored the nature of scattering by molecules, accounting for their polarizability. Polarizability is the capacity of molecules to form temporary dipoles. Raman reasoned that the molecules' interaction with electromagnetic radiation caused these dipoles to oscillate. These oscillating dipoles serve as secondary light sources, radiating light in all directions. A vital element of Raman's argument addressed competing explanations. He recognized the potential influence of dissolved impurities. He was rigorous in his attempts to mitigate their effect. Raman meticulously purified the water samples. He used freshly distilled water to minimize the presence of contaminants. He compared the scattering properties of pure water to water containing varying amounts of impurities. He found that the scattering observed in pure water was consistent with molecular scattering. This allowed him to discount impurity-based explanations. The immediate impact of Raman's work was the establishment of molecular scattering. This, in turn, provided a basis for understanding the color of the sea. His findings offered a plausible explanation for the blue hue. Other explanations fell short. These older theories could not account for the observed intensity and spectral characteristics. Raman's conclusion offered a physical justification for the observed color. His methodology and insights, furthermore, had a direct influence on the development of modern spectroscopic techniques. Raman's focus on the spectral analysis of scattered light provided a framework for this approach. His techniques became crucial in the study of light-matter interaction. These techniques have expanded into fields such as chemistry and biology. Raman's work laid the groundwork for later spectroscopic advances. The legacy of Raman's paper extends far beyond its initial scope. His work provided a new perspective on light scattering. The paper, furthermore, played a critical role in the development of oceanography. It contributed to the understanding of how light interacts with seawater. The paper's principles and findings are now integral to the study of marine environments. The 1917 paper, in essence, embodies a spirit of pioneering research. It demonstrated the power of careful observation and rigorous analysis. The work provided critical insights into light scattering. Its enduring importance is apparent in its continued relevance to scientific research. The paper serves as a testament to Raman's scientific brilliance.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.